we're on to the last section of chapter 2, 2.7, chemical nomenclature. So this is all about deriving names for common types of inorganic compounds using a systematic approach. Don't let the word nomenclature scare you. It just means naming. Those Germans. So nomenclature is literally a collection of rules for naming things. Sounds scarier than it really is. And compounds are identified by both their formula and by their name. So we're going to talk about how to name ionic and molecular binary compounds, which means composed of two elements. Ionic compounds containing polyatomic ions and acids. So ionic compounds, regular ionic compounds. Now this is, right now we're focusing on ionic compounds in the main group. We will talk about with transition metals in a slide or two. So the way you do it, you name your cation first, which is just the name of the metal, and then it's followed by the name of the anion, your non-metal. Okay, and then your anion, you take the element, you drop its suffix, and you replace it with "-ide". And if it's a polyatomic ion, you just use its name. So for instance, NaCl, sodium and chlorine. So Na, sodium. And then chlorine, we get rid of the INE and it becomes chloride. Ta-da! We're done with that one. We don't care anything about how many of part of it is. So CaCl2 is calcium chloride. Because ionic compounds combine in specific ratios where the name basically tells you everything you need to know. Okay, so here's some more examples. CSF is cesium fluoride. Ca3P2 is calcium phosphide. So phosphorus, you get rid of the orus and replace it with "-ide". Nitrogen, you get rid of the ogen and becomes nitride. Sulfur becomes sulfide. So you can see how these nonmetals names change. Iodide, bromide, fluoride, chloride, etc. Now, if we have a polyatomic ionic compound, if we have a polyatomic ion, it's very similar. So if I have this first guy here, potassium acetate, so K, potassium is my metal, okay, and then C2H3O2, that is a polyatomic ion. So if you're given just that formula and you're told name this, you see more than just two atoms, you have a polyatomic ion. So you go, okay, I got to figure out what this polyatomic ion is. And you look it up and you see that it's the acetate ion. When you have a polyatomic, you don't change it to "-ide, it just stays, it just keeps its name. So it's potassium with the acetate ion, potassium acetate. Okay, CaSO4, okay, Ca2 has a charge of 2+. SO4 has a charge of 2-. That's just the sulfate, sulfate ion. So this is calcium sulfate. Al2CO33, so that's 3 of the CO3s. This is aluminum carbonate. Same thing if you have a positively charged polyatomic ion. So NH4Cl, NH4 is a +1, it's an honorary metal. This is ammonium chloride. So this is still an ionic compound, even though there's not a single metal in it. It's because the NH4, you have a positive and a negative charge coming together. NaHCO3, sodium bicarbonate, and so on and so forth. Those are just some examples. Now, like I said, these have all been for ones where the metal only has one charge that it can be. So generally the main group elements. But the transition metals, most of them, and some main group metals, can have 2 or more cations with different charges. So that means we have to say what the charge of the metal ion is when we write its name. And we do this by using Roman numerals. So dust off your Roman numeral knowledge because you are going to need it. So we put the Roman numeral in parentheses after the name of the metal. So here's some examples. FeCl2. This is not just iron chloride. If I told you iron chloride, you don't know what the charge is on that iron, because it could have a +2 charge, or it could have a -2, or it could have a +3. So in this case, FeCl2, let's kind of break this down. FeCl2. Now we can do reverse crisscross here, and that makes sense. That means that the iron has a +2 charge, and Cl comes off as a -1, which is correct, right? The halogens, group 7A, group 17, have a -1 charge. They gain 1 electron. So this chlorine is a -1 charge. There's 2 of them, which means to cancel out the 2 -1s, we need a +2. So this is iron 2 chloride. FeCl3, on the other hand, is iron 3 chloride, because we have 3 -1s, which means this iron needs to be a +3 or to cancel out those chlorines. Let's look at this Hg2O. So mercury has some weird properties. In that Hg2 is actually, it's almost a polyatomic ion, but it's one of its ions that it can form. And I know it's really bizarre. And basically, what we can say here is this oxygen, well, we can do reverse crisscross. Let's just do that. Oxygen has that -2 charge, and that makes sense there, which means the mercury has to have a +1 charge. And then I have 2 mercuries, which means I have 2 +1s. So this is mercury 1 oxide. Mercury is weird, but that is how you do that one. Let's look at HgO. Okay, if we were to do crisscross here, though, it would look like it's mercury 1, and oxygen has a charge of -1. But it doesn't. Oxygen has a charge of -2. Which means that this mercury must be a +2 to cancel that out. So this is mercury 2 oxide. So these are just some examples. That we will come back to. Here's Erin Brockovich. Some of you have heard of this name. There was a movie made in 90s or early 2000s starring Julia Roberts about Erin Brockovich. Found that chromium-6 had contaminated the water in Hinckley, California. And it's present in the polyatomic ions of chromate and dichromate. Okay, so this is where that table comes in. So ionic compounds can often be present as hydrates. And what this means is a hydrate is an ionic compound that has water molecules bound within its crystals. So you've got like some different crystals in our structure here, and there's these spaces in between them. And in there we can put a water molecule. Okay. You can get rid of the water. You heat it up and you can dehydrate. The water will evaporate, and this becomes an anhydrous, meaning no water compound. So to name the hydrates, you start by naming the anhydrous compound, which is just the regular ionic. And then you add the word hydrate with a Greek prefix that says how many water molecules there are. So this is where this nomenclature prefix table comes into play. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. We'll need those later too. So you put the water on the formula when you're writing it out for a hydrate. It goes on the end. So you write your ionic compound formula, and then you put a little dot, and then you put the number in front to say how many waters there are. So for instance, copper 2 sulfate pentahydrate. So copper 2, so that means it's copper 2 plus, and then sulfate, SO4. And then if we looked at the table, we'd see this is 2 minus, which means, okay, this has got to be 1-to-1, CuSO4. So there's the copper sulfate. And then it says pentahydrate. So dot, penta means 5, hydrate, water. Calcium chloride monohydrate, calcium chloride dot H2O. You don't need to put the 1 if there's only 1. You don't have to actually write a 1. All right, so now let's kind of switch gears and talk about covalent, also known as molecular compounds. So these guys have a different set of rules for naming them. Okay, ionic compounds, pretty straightforward. The molecular ones, still straightforward, but different rules. And a lot of times people start getting them mixed up once you add these into the mix. So make sure that you first identify if you have a molecular or an ionic compound before you proceed, and that you remember which rules to use. So in covalent compounds, electrons are being shared, and because of that, you can actually have different ratios of atoms being bonded to each other. Whereas an ionic compound, there's always one sodium for every one chlorine. Not necessarily the case with a molecular compound. These guys can have different ratios. And remember, molecular compounds are non-metal to non-metal. So we actually have to explicitly identify what these numbers are in a molecular compound name. So the way that we name these is the non-metal that is the most metallic, aka the one furthest to the left. Doesn't mean it's a metal, it just means it's the most metallic-like, and we'll talk more about that when we talk about periodic trends. That comes first, and we just use its full name. And then the next part of the name is the least metallic, or the one furthest to the right or furthest towards the top of the periodic table. And then we change its ending to "ide," just like we did with the ionic compounds. And then we have to use those Greek prefixes like we did for hydrates to specify the numbers of each atom in the molecule. When the first element, if there's only one of it, we don't worry about using mono. Okay, and if you have two vowels next to each other, so like for instance, you have 5 oxygens, you get rid of like the A. So it wouldn't be pentaoxide, it would be pentaoxide. You just get rid of the A. We're going to look at examples because this makes a lot more sense when you look at examples. So SO2. Okay, and in general too, if you're given the compound formula, you already know which one's going to come first in the name. Okay, so S, sulfur, so that doesn't change. And then I have 2 oxygens, so di meaning 2, and then oxide. So oxygen, we get rid of the end of it and it becomes oxide. And then we have SO3, sulfur trioxide. Again, notice there's only one sulfur in both of these, so we don't say monosulfur. If it's just one, just leave it as so. But that's only for the first word. NO2 is nitrogen dioxide. N2O4 is dinitrogen tetroxide. So we get rid of the A. It's not tetraoxide, it's tetroxide. N2O5 and dinitrogen pentoxide. Let's see. There's a bunch of different ones. BCO3, blah, 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 blah. Here's one. NO. Nitrogen monoxide. So when you only have one, but it's the second element, you need to use mono. So this is nitrogen monoxide. So now let's talk about naming acids. Some compounds containing hydrogen are a member of the acids. And these guys release hydrogen ions when dissolved in water. So one way to know if you have an acid when it's dissolved in water is it has H first in the formula, something like HNO3. So when you add an acid to water, before it's added to water, it is not really an acid. It becomes an acid when you put it in water. So when this happens, when you have an acid and water mixture, it's given a special name to say that it's an acid. So a binary acid means you just have hydrogen plus one other element. Okay, for example, HCl. Okay, so when you see, if you were to see HCl and then in parentheses AQ, AQ means aqueous, so that means it's in water. So we take and we change this to hydrogen, or take hydrogen, change it to hydro. And then we look at the other element, in this case Cl. So instead of chlorine, now it's chloric. So we get rid of the ending, change it to ic, and then we add acid at the end. So this is hydrochloric acid. Whereas normally HCl, when it's just HCl by itself, when it's not aqueous, would be hydrogen chloride. I know it seems a little weird because hydrogen is not a metal. HCl is technically not an ionic compound, even though it's weird. But we just we name it as though it's an ionic compound. So here's some examples of some simple binary acids. You can see it's just hydrogen and one other atom. H2S, that's still binary. It's just hydrogen and sulfur. It's hydrogen sulfide. We put it in water. It becomes hydrosulfuric acid. So sulfur is one where its endings are a little different. Okay, it goes from sulfur to sulfuric. So we actually don't drop anything off of sulfur. We just kind of add on to it. So then we have oxyacids. So these have hydrogen, oxygen, and at least one other element. So what way to know if you have one? You look for a polyatomic ion. Okay, so to name them, we get rid of hydrogen. We do not have the word hydrogen in it. We start with the root name of the anion. So, and then then we have, you're going to look at your polyatomic ion, and you're going to look at what it ends in. If it ends in ATE, so sulfate, you get rid of the ATE, you replace it with ic. So sulfate, well, sulfate becomes sulfuric, but still the 8 becomes an ic. If it ends in ITE for ite, it becomes OUS or us. So here's how I have always remembered. Well, I made this up recently, but now I remember it like this. I ate something and it was icky. Scheiße. Okay, ate to ick. I ate something, it was icky. And I'm so full, I have the itis. Something I remember we used to say when I was in high school. Oh, I've got the itis when I was full. I don't know if the youth say that nowadays. But itis. Ite to us. I ate something, it was icky. Ate to ick. And then you add acid to the end. So we'll look at some examples. So for instance, HC2H3O2. We look at this and say, okay, there's the H, draw a little line there. And I look at my table, I see C2H3O2. That is the acetate polyatomic ion. So that means this 8 becomes an ic. So now this becomes acetic acid. HNO3. NO3 is nitrate. It becomes an ic, so nitric acid. HNO2, NO2 minus is nitrite. So ite becomes an us. So this becomes nitrous acid. HClO4, perchlorate, becomes perchloric acid. Like I was saying, let's go down to the sulfates. H2SO4, SO4 is sulfate, and I was saying sulfur ones are a little different, becomes sulfuric, but it's still 8 to an ic, so it's sulfuric. Sulfite becomes sulfurous. Phosphate becomes phosphoric, so kind of like sulfate. The phosphorus ones are a little different. And that's how we name acids. Once you get the hang of it, it's not too bad. The nice thing about doing this online is you basically, the world is at your disposal for the interwebs and your lecture stuff. So I thought we'd just kind of do a couple little practice problems. These are from the end of chapter exercises, which don't just do the homework I assign, guys. That's for points, but I highly recommend doing the exercises in your books for extra practice. If you need help on them, please know you can reach out and I will give you as much assistance as you need. So here we want to write the empirical and the molecular formulas. Oops. So the molecular formulas, I'm going to kind of make this as a little chart, and then empirical formula. So for A, molecular formulas, we see we have 1, 2, 3, 4 carbons, and 1, 2, 3, 4, 5, 6, 7, 8 hydrogen. So there's my molecular formula. Empirical formula, remember, is the lowest whole number ratio. So if we divide both by 4, this comes out to be CH4. Our next guy here, we have 1, 2, 3, 4 carbons and 6 hydrogens. We can divide both those by 2 for the empirical, and this becomes C2H3. Next, we have silicon, 2 silicons, and then we'll go to the chlorines next. There's 4 chlorines and 2 hydrogens. Everything can be divided by 2 there, so this is SiCl2H. It's a weird compound. And now we have this next one, starting from the center, we have a P, and then we have 4 oxygens and 3 hydrogens. And that is going to also be the empirical formula because we can't divide by anything to make it lower. And I believe that concludes chapter 2. Just a reminder, either on the videos, in the Q&A, whatever it may be, please make sure to post your questions or email me questions you have on the homework from your book, anything you want me to elaborate on to do later this week. I'm going to continue to do it where I try to post things either Friday night or Saturday morning, answering your questions to help you guys so you have all your homework done by Sunday. I hope you are all staying safe and are doing okay. Please remember you can still contact me with any questions or help you may have or need. And I will see you all soon.